Hello and welcome everybody to Advent of Code 2023 Day 18. So I had a very busy weekend just gone, so I've skipped Day 17. So I spent a little bit of time working on it, but I didn't get it implemented fully, so don't have a video for that one yet. But I decided that I try and keep up to date with the ones I have had time to look at, so we're jumping in with Day 18 now. So I'll come back to Day 17, release a video for that one whenever I get it done. So anyway, day 18 was it was pretty fun. It's nearly identical to day 10 to the extent that there's definitely some people who were able to use exactly the same approach for day 10 as for day 18, which is kind of interesting. There is a smart but limited working approach if you were to use flood fill for day 10. But then if you try to do that on this one, it's not going to work. So the flood fill approach for day 10, there were some people that kind of expanded the grid out and then were able to use flood fill to calculate the size, but that won't work for this problem. But there is another kind of mathematical solution for it, which will work perfectly for all of these. I actually have two different implementations. So I have my first implementation, which is actually the way that I did day 10. I did improve it though, performance-wise, just a couple of tweaks to my algorithm. And then the second part, I used that mathematical one because even with the performance improvements from my first part, there was no way that it was going to work for the second part. The numbers that you end up dealing with are just enormous. So using the little bit of maths solves the problem quite easily and extremely quickly. So with all that said, let's jump into the problem and see what it's about and look at some code. So day 18, lava duct lagoon. So as we've been going through this, we had a lava fall that we had from the lava island down onto the metal island. So the factory needs a very large supply of lava, so the elves are starting construction on a lava lagoon. So they basically need a big, massive area where they can put all this lava into, and they'll be able to use that to power their factory. So while they've started to work on this, they have this dig plan that they have together, which is here, and this is our puzzle input. So what we're told is there's an elf in a digger. And he starts at some point, and from there he's going to follow this pattern, and he's going to dig a trench following these coordinates. So if you scroll down, you'll see here these hash marks map out the trench that he's going to dig, which will be the outer boundary of this lava lagoon. So once that's done, once the trench is dug, he's then going to dig out the interior of all this. And so that's concept of what we're trying to do. And what we're asked to do is we're asked to figure out what the total amount of lava that this could hold is. So it says cubic meters. We're told that each of these squares is going to be 1 meter deep, and they're 1 by 1. So each one of these cells, if you were to count it, is 1 cubic meter. So then the whole lot, if you basically add up all of this all together, you'll get the total area of it. So you might remember from the part 10, we ended up with a shape very similar to this when we followed our pipe map. But what we were specifically told with that one was that you didn't want to include the actual pipe work itself in that case, in which case that would be the hashes here. You just wanted to know what the internal bounding area of this was. And that is... So it's a slightly different problem, but when you look at the maths and stuff for it as well, their two are very distinctly related, and that's a trick we can use to solve this whole thing. But so the first thing we can do is, with this relatively small data set, we should be able to go through all of this, and as we're going through it, we'll be able to count the total number of cells are in our trench, and then if we're then able to figure out the total number of points that are inside that bounded area, we'll add the two of them together, and that will give us our total area for the whole trench. So yeah, that's roughly what we have to do. So let's see how I did it for part 1. I'm trying to think. There's a lot of code here. It's not super long, but there's some of this as well we can ignore because some of it's just some visualization code that I had written for debugging. But let's see. Okay, so we'll start at the top and we'll go down through it. So this is just setting up some data structures, just some points to know maximum and minimums for X and Y values that we'll find, a map which is going to contain all of our points, so the X and Y coordinates of every single point, which is possible for the first part, because the amount of points we generate, the total length of that path isn't that big, so it's okay just to store it in memory. And then, yeah, this grid is just my data model that I use for the visualization, so we can ignore that. This corner lookup thing, yeah, we'll come back to that in a second. And yeah, okay, so then the first part, how we start this whole thing off is I'm basically going to build this map that's going to contain every point that's in the boundary. So the way we do that is I go through the whole line, so each dig line, and I take that dig line, I'll say, okay, it starts here, so then that's going to, I know what that coordinate starting at is, it's going to be like 0, 0, and then we're going to go, so say if it says it's right by 6, we're going to go 1, 2, 3, 4, 5, 6. So I do that loop here, I take that distance, iterate that many times, and insert a new point for each of those into my map. And each of those is going to be part of this boundary then, as we go through. So the values that I insert are these, they're U, D, L, or, which just tells me, so this is just how I can lay it out. So in question 10, these were like the vertical pipe and the horizontal pipe, and then there was the 90-degree bends, so there was different types of 90-degree bends. So that's what this is for up here, so bear with me. And yeah, that's really it. I'm just updating the maxes and the mins here as I encounter new X and Y values. And yeah, that's it. Oh, and then there's another data structure down here, which is just for every Y coordinate, I'm trying to assemble what the max and the min X value is for that. So if you were to just scan this as a grid, line by line, for every Y, I just want to know, well, where along that are the X and Y bounds, which we'll use that later on. So I can assemble that in here as well. And yeah, so then the corner lookup thing. So this is a little bit funky, but if you imagine, so we don't have those corner pieces like that are already pre-generated like the part 10 was. So we sort of have to generate those ourselves. So I'm actually using the exact same list of them, except I have to use a small L because I already have a big L in here. But I could have changed these. I know I could have changed these to the symbols he used in the previous example, but doesn't matter. It was a bug I found as I was debugging it, and I was like, I'm not changing this, I'm just going to update this. So it still works, it's fine. But yeah, the whole thing here is, so this is how we determine. So if you were to draw the grid, and you'll see it, so let's say like here, we'd have like or, which we get to here, and then suddenly we'd have D, 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 D. So we know or D is like a chain, a pattern, and we know that that should be a 7. So that, because that should be in from the right and down one. And so that's what I have here. I've got or, D, and 7. And yeah, there's 8 different cases of those that are the different combinations you can have. And these are just the corner pieces that then match those. And the corner pieces become important later on. You'll see why. It's the exact same reason why they were important in number 10. So but anyway, we'll move on. So keep going down. So we've iterated through our whole file. So then, yeah, this is the guts of the algorithm that actually solves this problem for us. So this is, if you remember from my part 10, this is a method of determining if a point is inside or outside of any given polynomial, as long as you know the bounds of the polynomial, which in this case we do. And so the way this works is you start from some point outside the polynomial. So if we have, I'm going to say our circle is our polynomial. So we start at some point outside it and we start iterating through. When we cross the boundary of that polynomial, we increment a counter to say that we've crossed that boundary. Then we keep counting, so we keep moving inside the circle until we get to the far side of the circle. We cross that boundary again, and we increment a counter again, and then we keep counting. Well, so we can stop at some point, or our stop point might be inside the circle, or it might be outside the circle. It doesn't really matter. The key is that, the trick is that for any given point along this line, if the count of the times that you've crossed the boundary of the polynomial is odd, then you're inside the polynomial. If it's even, then you're outside the polynomial. That's it. So these mins and maxes come in handy here, because for any line, I just want to know. So I'll start at just one outside the boundary of it, and then I'll finish one outside the boundary of it. So that's just how I know that. So I'm not wasting iterations going from 0 to some arbitrary large value. And yeah, that's it. So each y coordinate will do this loop to go through all of the x coordinates. And we basically need to do our boundary check. So the real key to this is the boundary check. And this is how we do the boundary check. You need to determine if you've detected a one of the boundary pieces, but the direction is important. So if you detect any vertical, so that's the just pure up and down ones, then you know you've crossed the boundary. But if you detect a corner piece, you need to specifically do a certain pattern, and that is either the corner pieces that are going in and up, and the corner pieces that are going down and out. And that will work for this case. The other case you can do, which also works, is the opposite direction of that, the opposite version of that. So you can look at, so if this is J's and L's, you can also look at, F's and 7s, and that will work too. But you can't do both, you just have to do one. So it's basically like, there's like a handedness to it. So you just have to make sure that you're only checking those ones. I talked about that in the video number 10. That's the real trick to make this algorithm work. And yeah, that's kind of it. You go through every single one of these, you do the counts for each point that you encounter, you check that count at that time, and you say, and if it's odd, then you're inside, you increment that counter. And then at the very end, you'll see if we're inside it and we've incremented that counter. So we're inside it, so we have the total count of all the points inside, and then in this case it's just the total amount of boundary points summed together, and that gives us our answer for this problem. So this works relatively fast. If I run it for 18 plus 1 on the sample, should run in, what? Oh, sorry. Run 18.1 sample. There we go. Yeah, so there's and that's a little visualization I put it there. So this is our thing as it moves around, and then the red stuff in the middle is all the internal pieces we found, and you can see here these are all the boundaries. So in our case, like I said, we only encounter J's and small L's. We use those to count our boundary things. So you see there's a J, so we start a count there. So otherwise this stuff would mess us up where you had straight lines along here. So we can ignore the F, but we count the J, and we'll count 1, and then there's nothing else, so we know we're on an odd. So that works fine. And the same would work the other way around. If you counted on the F's instead, then you count F, and then you can ignore these because they're part of the boundary. So then we encounter this one, so we know we're on an odd number again. So we count 1, and then we encounter an F, and then we can ignore the rest of these. And then if we got out here to test those ones, they'd all be outside as well. So that works. That's fine. I'm just going to comment this out because the visualization, or just change this to false because the visualization for the main one isn't easy to render on the screen here. So, but I can run that for the input, and you'll see it also runs pretty quickly. Yeah, so few milliseconds. And that works pretty well. Now, you could be fooled into thinking, because that runs quite fast, that this will work just fine for the part 2. And depending on the numbers, that might be the case. But for our part 2, the numbers are they're huge. So this is just not going to work, this algorithm. Even though this is pretty speedy, the algorithm is not going to work for the part 2. So let's have a look at part 2, and then let's talk about the slightly more mathematical approach that if you know it already, it'll be very fast for you to do. This whole day would have been super fast for you if you'd just done it like that from the very start. I knew of this algorithm to do it. I knew that I'd be able to solve it even if the numbers got big, but I specifically wanted to re-implement my day 10 solution and make it a bit faster, which is why I spent time doing this bit. But anyway, let's have a look at that part 2 then. So for part 2, they tell you basically it's the exact same thing. So they say that so they've realized that the area that you've told them for this lagoon is way too small. So someone figures out that they've actually read the instructions wrong, and that it's actually a little bit more. So there's a different set. So what they said originally in our instruction set was there was this hexadecimal color, which is not a color at all, it seems. So what this actually is it's a hexadecimal encoded version of the same instructions that we previously had. So where can we see? Yeah, so the first 5 digits we're told of the hex number, we're told are the value, the distance value, and then we're told the last digit is the direction. So the last digit will always be between 0 and 3, and each of those corresponds to right, down, left, and up, respectively. So when you do that little bit of parsing logic, you end up with this set of instructions instead of what we previously had. And you see these are some pretty big numbers. So if you start just iterating through this, you're going to be there for a very long time. So instead of doing that, this is where we can use our mathematical approach to solve the problem. So let's have a look at the code for that. So you'll see it's a lot cleaner, a lot less verbose. And yeah, the main body of this entire code is just parsing out the actual input itself. So basically there's 2 pieces of maths that you need to know for this. One is the shoelace formula, and the other one is Pick's theorem. So the shoelace formula basically is a method by which you can, if you have a polynomial made up of, and you know all the corner points of it, so you know all the vertices of it, this formula, you can iterate through all of those points, and you can sum them together in a way that will give you the total area of that polynomial. Then the second piece of math you need to know is you need to know Pick's theorem. So Pick's theorem is a theorem that basically relates the area of a polynomial to some function of the count of its internal points and the count of its boundary points. And with those 2 pieces of information known, it will give you the area of the polynomial. So what I've said there is I've got 2 formulas that both have area involved in them. So if we use the first one to compute the area of the polynomial, then we can use the second one to try and figure out the internal and external points stuff. So the first thing we have to do is we have to create an array of all the points. So we can do that in our parsing logic. It's fairly straightforward. We start off with an initial point of 0, 0, which is our very start position. And then we'll iterate through this whole thing. We're going to keep a log of the value of the boundary points, just a sum. So we just add that distance that we parse out each time to the boundary point sum. Then we'll have some new xy coordinate that we're going to derive for each direction that we go. So we have our 4 directions, and then this is basically what the new point will be based on the direction and based on the distance that we traveled. So if we're going to the right, we're going to be x plus that new distance, and y coordinate will stay the same, and that pattern then holds down for all of them. So that gives us our list of points, and then we do this loop, and this loop, basically, this is pretty much Pick's theorem, so, or pretty much the shoelace formula. So it's these, so if this is 2 points, x1 and y1, so x1, y1, x2, y2, then this product, so the sum of this product for all these points in a row, half of that will give you the use your words, Ian. Will give you the area, and then basically this is just a rearranged version then of Pick's theorem, which ultimately gives us the answer that we want in the end. And this runs extremely fast. So we can do run 18 to on the sample, runs in a few microseconds, and then for the input, a handful of milliseconds, and that's both parts done. And this will then also, this exact thing works for the first part as well, and it will be even faster again because the data values are so much smaller. But ultimately the only thing that changes to make this much slower is just the number of points you have. So if you have a very large amount of points, obviously there's just more loops of the computation, but it's kind of trivial, really. The difference is the sizes of the numbers themselves of the values of those points don't make that much difference. It'll just be the number of points that make a difference for its efficiency as you scale it. So that's about it, really. Just a fun one today. If you know this little bit of maths, again, you'll be set up very well to do it. Otherwise, it'll be a little bit mysterious, but a little bit of research then will show you some good ways of doing it. I don't think I have much else to say about this. I kind of glossed over the maths in this specifically. I didn't throw up any formulas, but if you want to convince yourself of this approach, go and have a look at the shoelace formula and Pick's theorem. Literally within the first few paragraphs of each of those wiki articles, you'll find all the information you need to basically confirm this or convince yourself of this formula. So that's it. I'm going to go off and have a look at day 17 now, spend a little bit of time on that. So you may be getting a second video today. I don't know. And aside from that, if I don't see you in day 17's video, I shall see you tomorrow for day 19.